So I have two things to say. The first one with a deep regret. This is the last lecture of the conference, but now I have a great pleasure to announce the lecture, the talk by Rajesh Gopakumar from the International Center of Theoretical Studies of Mangalore, and the talk with a tantalizing title, Deriving Gauge String Duality.
Thank you very much. Unlike all the previous speakers, I will not begin my lecture by thanking the organizers. Rather, since this is the last talk, I will end the lecture by thanking the organizers. So, hopefully we'll be able to acknowledge all the people who contributed to making this a success. So, but yeah, more about that later. So I'll try to give you a little bit of a snapshot on an ongoing effort to understand in some, at least from a physics point of view, understand better this tantalizing gauge string duality that has been around for many decades and gone through successive stages of evolution. Much of the work I will talk about is jointly with Matthias Gaberdiel, who is here in the audience, but some of the work I will focus on, especially in the last year or two, is also with a number of other young people listed here. So this is the broad outline of the talk. I'll try to motivate first what I really mean when we are talking of deriving gauge string duality or ADS-CFT. And then I'll sort of outline a bit of a philosophy, this reference to Grothendieck's program is not gratuitous. It's in some ways, perhaps there's even a connection which I might allude to briefly, but it's a philosophy to try to understand how a theory of worldsheets, in one way of thinking of string theory, might arise from a theory of world lines, like a larger gauge theory. But that's sort of more philosophy. As people say, show me the money. So I'll try to sort of illustrate it with a particular example where I think we now understand fairly well the way in which all the pieces sort of come together. So this is an example, one of the canonical examples of ADS-CFT duality now in ADS3 and dual to a two-dimensional CFT. And we'll look at this correspondence in a very specific limit, the tensionless limit from the string theory point of view, or the free theory from the CFT point of view. And here we'll try to illustrate, and that's what I'll mostly focus on in this talk, how this sort of philosophy is sort of realized in trying to go from world lines to world sheets. But we will be in the happy situation where we can actually close the circle and see how it fits in very well with if you were to try to go the other way around from the string theory to the field theory. And then if time permits, I'll say a little bit about what this holds for other examples, particularly ones that physicists would find more interesting, four-dimensional Yang-Mills, or at least free super n equal to 4 super Yang-Mills. So that's the broad roadmap. So the question is, how exactly, I mean, this is a question that has been there for nearly half a century now, about how exactly do large N gauge theories initially, but more broadly, large N quantum field theories in some ways reorganize themselves into theories of strings. There have been many tantalizing hints, which I think it's fair to say that probably it's about a quarter of a century ago that we got most concrete sort of a handle on this. And this was the genesis of the ADS CFT duality, where the insight was through string theory, through objects like D-branes and string theory. We see these two dual pictures of the same, in some sense, the same theory, and it's really an open-close string duality, where the open string picture of D-branes and the sort of the picture of D-branes as sources of gravity, they are essentially, I mean, the consistency of the theory requires them to be the same picture. And if you wish, you can sort of pictorially think of it as a case where all the holes of the open string worldsheet in some way close up to give you an equivalent closed string description, perhaps about a different background. So this is the picture here, and this picture, of course, arose or could, I mean, the original construction, in some sense, was obtained by looking at the theory in a limit around flat space, or in some way in the strong coupling limit of the field theory. So in some ways, you're sort of summing over an infinite number of holes and weighting these holes with some power of the Stoft coupling, G string, the string coupling times n, the number of D-branes or the rank of the gauge group. So while this picture has always been there, it hasn't been easy to make this precise or indeed go beyond the D-brane constructions that that one can control. So I'll try to make the case that in some ways you need to sort of shift your lamppost if you wish. If you want to reduce the parameter space of gauge string duality to its bare essentials, it's essentially a two-dimensional plane with the vertical axis sort of measuring the quantumness of the string theory, or quantumness of the string theory, which is why this parameter G string appears here on the vertical axis, but that's equivalent to going beyond the so-called planar limit in the field theory. So that's the vertical axis, about which actually I'll say very little. I'll be more interested in the horizontal axis, which measures, if you wish, the stringiness as opposed to the quantumness. So I'll be working in some sense in the classical string limit, but here one can still dial a parameter, this Stoft coupling that appeared in the previous transparency, and the regime of very strong Stoft coupling is where Einstein's theory is and corrections are applicable, are reliable, and that, of course, is a regime of gauge theory that you normally can't access, which is why it has been wonderful to have ADS-CFT tell you about all kinds of amazing things at strong coupling. But there is a regime of the gauge theory which we do understand, which all our quantum field theory textbooks are all about, which is the perturbative regime when this coupling is very small. And this translates through this dictionary to the dimensionless parameter lambda, essentially measures the curvature of the background, the ADS background in string units. So this is, if you wish, the most curved. It's the highly curved, or equivalently the tensionless limit. And this is the sort of lamppost I would like to shift attention to. So as I said, we understand the field theory, but not necessarily the bulk, because it's highly curved. And at least we don't always have good sigma model descriptions of the string theory in this regime. The dictionary, as I said, is usually in the ADS-CFT that the radius of the ADS, or the inverse curvature, is proportional to some positive power of the Stoft coupling. And this is why this corresponds to a high, the lambda goes to 0 corner is a highly curved regime. But the nice thing here is that if you go back to that picture of these holes, in the perturbative theory, there are typically a finite number of holes that you have to sum over. For instance, to a correlator at, so to say, in the free theory, there's just a finite number of Feynman diagrams, and which also, of course, have a well-defined genus expansion. You can go up along this axis as well, and the perturbations are expected to be also, going away from this free point is also, as quantum field theory textbooks tell you, is essentially an exercise in free field theory or weak contractions. So understanding free correlators should be a good starting point to sort of move away from this corner and understand the duality in this regime. So we'll focus on mainly this first test case here, the ADS3 CFT2 duality, and the CFT2 in this case will be a sort of a free orbifold CFT, a symmetric orbifold of, let's say, n copies of the T4. And in the limit where n goes to infinity, there is, of course, the ADS5 example, and there we are talking about perturbative n equals to 4 Yang-Mills, about which I'll say something at the end, hopefully. So firstly, what do I really mean by sort of a derivation? So the operational sort of point of view that I'll take is that a large part of the ADS-CFT dictionary, the correspondence, is a relation between correlators on both sides of the duality. So on the field theory side, you talk typically of gauge invariant correlators, which are, so to say, single trace, which correspond to, in a Yang-Mills theory, a trace of a large number of fields. So we'll look at it in the Euclidean case. So they are on the boundary of the ADS, so which is a d-dimensional sphere, and these x's are coordinates on that sphere. These labels, the labels H would refer to the conformal dimension when we are talking of a free theory, which is sort of so you can label them by conformal dimensions, and these W's are additional labels, which we'll come to. So the claim is that if you look at correlators like this and then extract the genus G contribution through the 1/n expansion, then the claim is roughly that there is a string theory correlator on the right-hand side, which in the best circumstances would be given by endpoint function again of physical string vertex operators, perturbative string vertex operators, which have the same labels as the operators over here. But these are now inserted at specific points on a string worldsheet. So those are these coordinates Z, but they are the X's, which are the space-time coordinates here, are just, labels from this worldsheet point of view. So these are a set of vertex operators which would correspond to these operators. So we need, before we can write something like this down, we firstly need a kind of a correspondence between physical states of the string background and gauge invariant single trace operators of the field theory. So this the statement is that if you now consider the endpoint function, again on some genus G worldsheet, and then integrate over the moduli space of these worldsheets, you should reproduce this gauge theory correlator. In some ways, this is probably as mathematically well posed as you can make it, in the sense that the left-hand, these are autonomously well-defined quantities on the left-hand side as a field theory, let's say at some conformal fixed point, or in the case we'll be mostly considering a free theory. And on the right-hand side, again, you in the best case you would have a perturbative two-dimensional sigma model describing the string worldsheet theory, and this would be a correlator, a physical correlator in that theory. So the whole idea here is not, of course, to check this, but to try to make this equality manifest in some sense, to try to tautologize it so that you see why the field theory really is assembling itself into a string theory. So that's the broad goal. So let me try to sketch the broad philosophy first. So when I wrote this, down here, there seems to be an apparent asymmetry in this equality, because it would seem that if I knew what the string theory was, then in some ways I can compute this quantity and try to show how it might be equal to a gauge theory quantity. But it seems less obvious that you can go from the field theory side, namely the left-hand side, to the string theory side on the right, because it would seem that you need to reconstruct a worldsheet integrand if you, which of course wouldn't be unique, but you might hope that there is perhaps a canonical or a natural form of the correlator on the right-hand side, so the philosophy here is to try to recast the Feynman diagrams here in a way which would give rise to some kind of a canonical integrand or a correlator on this side. So when I said that there's an asymmetry, it's a bit it's a bit misleading, because even on the left-hand side, if you view a field theory correlator in terms of Feynman diagrams, there is an implicit sum over world line topologies, which is what Feynman diagrams are. So the Feynman diagrams for large N theory, you do have a sum over here, and on this side you have the sum over all the distinct worldsheets, the moduli space, and the idea will be to actually identify the summands, if you wish. So in a sense, if you want to condense it to a slogan, the idea is that each Feynman graph corresponds to a point on the moduli space, a particular closed worldsheet, and the idea here is to exploit a very nice parametrization of the moduli space of Riemann surfaces due to Strebel, and which actually appeared in Koncevich's famous proof of the Witten conjecture. So this, I'll very briefly outline what this parametrization is, but in some sense, for the moment, if we exploit this parametrization, what we will do is essentially assign to each worldsheet a sort of a point on the moduli space, and in some ways, this is a refinement of Toft's idea, in which, of course, there was a natural assignment of the genus of Feynman diagram, or these ribbon graphs, to a genus G worldsheet. This is sort of pushing it one further level. So maybe let me just briefly mention what the Strebel parametrization is. It's a mathematical theorem that there are these unique meromorphic quadratic differentials on any Riemann surface, which have a rather amazing property that they foliate the Riemann surface into into closed horizontal trajectories, which are what are drawn here, something like isotherms. So the horizontal trajectory is defined as something where phi dz square is positive. The idea is that if I look at these lines, they form closed trajectories, and moreover, they foliate the whole Riemann surface into disk-like domains, which are separated by a kind of a graph, what's called a critical graph. This graph is a graph whose vertices are the zeros of this meromorphic differential, and whose edges are each of which is a disk domain which contains a single double pole. So these meromorphic differentials have double poles at the marked points, which I've denoted by ZIs. So the zeros are denoted by AIs over here, and the marked points, which are the double poles of the differential, are marked by ZIs. And the theorem of Strebel is that these Strebel lengths, which correspond to if you wish, measure the length of the edges of this graph, these are real for a Strebel differential, firstly, and you can use them to they give a kind of a real parameterization of this decorated moduli space, namely the moduli space of genus G with n punctures times a factor of r plus to the n, where this is a rather trivial factor, which corresponds to just the residues at each of these double poles. Now, so the idea in this philosophy was to sort of, in some ways, associate these Strebel lengths to the world lines. And certainly, one aspect of the Strebel lengths, when you try to associate them, or rather, you associate the dual to this critical graph to the Feynman graph of the original theory. So if you wish, in trying to glue this simple case, you're sort of gluing it along this junction here, and this is the Strebel graph, and it's sort of the dual to the original Feynman graph, and these are the original ribbon graphs, which are essentially pieces of this Strebel foliation, which I'll show in the next slide. So the Strebel lengths, in fact, you would, because they are, as I'll show in the next, maybe become clearer in the next picture, if you identify this Strebel foliation with the Strebel graph with the dual to the Feynman graph, it's natural to associate the length to the number of big contractions between the vertices. And in the simplest case, where the Strebel lengths are these integers, those correspond to very special points, discrete points on the moduli space, which actually do appear in the descente d'enfant. But let me show a picture which will sort of make this maybe a little clearer. So the idea is that if I have a Feynman diagram, and these are the weak contractions between the Feynman diagrams of the free theory, then you sort of identify you identify these with the so-called vertical trajectories, which are orthogonal to the horizontal trajectories, and you glue them. So each of these forms a strip which goes from a pole to a pole. So you can see this is sort of, this quadrilateral here is conformally equivalent to a strip, and it's foliated by these horizontal trajectories, and the orthogonal trajectory is this original Feynman graph, which is the dual to the critical graph over here. So the idea is to glue up these strips to form a particular point in the moduli space, and that is the dual close string, the point on the moduli space corresponding to the dual close string. So, okay, so as I said, this is sort of philosophy, but let me try to illustrate this in this example of the tensionless limit of the ADS 3 CFT2. So there, we were very fortunate that we had this very simple example which illustrated these ideas very well. It's built on something which, with Matthias and Lawrence Eberhardt, we fleshed out in a few years ago, that the string theory on ADS 3 times S3 times T4 with 1 unit of so-called Nebus-Schwarz flux is by the ADS CFT correspondence. We claimed dual to the free point of the symmetric orbifold. As I mentioned, it's the nth symmetric power of T4, orbifolded by the symmetric group acting on all the copies in the limit as n goes to infinity. So, so in this case, you, as I said, I'll try to illustrate how in this case you can see very explicitly that the Feynman diagrams, if you wish, of the gauge theory correspond to the points of the moduli space of the string theory that contribute to this correlator, and in this case, as I said, we'll be in the happy situation where we have control over the dual worldsheet theory as well, and we'll see exactly the same phenomena. So it's no longer, in some sense, a guess. It sort of fits together. So let me explain to you how this works in the context of these correlators of this orbifold CFT at the free point. So this is the CFT. We'll mostly be considering correlators of this form in the CFT. So these are, this being an orbifold of a two-dimensional CFT, the states are labeled by the twists, and the so-called single particle states correspond to ones where there is a single cycle of the element of the symmetric group is labeled by a single cycle of length W, and that's what this W label here is. So W equals to 2 is the sort of Z2 twisted cycle, and so on. So we'll consider the ground states for simplicity of this W cycle twisted sector and an arbitrary correlator, an arbitrary endpoint function. Now, it has been known from 2000s that there's a very clever way to compute these correlators in this CFT, and that's by going to an auxiliary covering space. So if you started with the theory on the two-sphere and you had these insertions of these operators, you could go locally to a covering space such that you lift the so these are multi-valued fields. I mean, these are twist operators, so the fields are multi-valued on this base space. You can lift them to this covering space where they become single-valued. So they become single-valued, but at the expense of introducing these multiple sheets and branch points at these at the pre-images of the location. So you so the nice thing that Lunen and Mathur observed was that, for instance, if you lift it to the covering space, essentially these operators become trivialized on the covering space. They just become identity operators. But now you have a non-trivial covering map which carries the data of the branching or the twisting. And so locally around each of these points with a cycle Wi, you have a branching of order W. And then you have to put all these together. So globally, this is actually a rigid problem because these are the only branchings. And so you need to find, so the problem of computing this correlator reduces to finding a covering map, a holomorphic covering map of your original sphere on which you're computing your correlator, a covering map which has a fixed branching at these points xi. And you can easily convince yourself that this is a rigid problem in the sense that n minus, let's say we look at a covering space whose genus is also 0, then you can convince yourself that you, apart from 0, 1, and infinity, the n-3 other locations of these ZIs are completely fixed. And probably this will become a little clear when I write it out a little more later. But in any case, this is a rigid problem. And so you get a very specific, discrete set of covering maps which will contribute to this correlator. And so you just enumerate all these correlators and you attach a weight to them, which is essentially coming from the pullback of this covering map and the conformal anomaly factor that comes from pulling the CFT from here to this covering space. So this, in a way, is a very elegant solution to computing correlators in the free orbifold theory. And it is this that we will exploit together with another observation again made over a decade ago, that to each of these covering maps, you can associate a Feynman diagram-like interpretation. And that's as follows. If I, let's say, take a 4-point function on my original base space, I draw some closed curve going through these 4 points. Let's say I draw a solid curve which encloses infinity, and then I sort of also have a dashed curve on the complementary hemisphere. And then I look at the pre-image of this on the covering space. I'll get something like this, because this is sort of a threefold cover. So there are 3 pre-images to infinity, which is this black dot here. And so there will be a sort of a, in the physics language, a bifundamental like double line graph, and with the number of edges that come out of any of the pre-images will be there'll be 2 WI edges, and overall there are n pre-images of the infinity given by the Riemann-Hurwitz formula. So I just singled out infinity over here because it'll play a role. These are the poles of the covering map, the points which map to infinity. And so you can view this graph as sort of triangulating this covering space, and we'll see that indeed this is sort of the 't-Hooft-like worldsheet of the dual string theory. But the rigidity of the problem that I mentioned last time means that to each covering map, there will be a Feynman diagram, and it will correspond to a distinct point on the moduli space. So there'll be, to compute the full correlator, I have to sum over all these covering maps, or equivalently over all these Feynman diagrams, or equivalently from, as we'll see, sum over all these distinct points on the moduli space, which contribute to this correlator. Okay. So if we, the problem of, so this is of course a good in principle solution of the problem, but to actually calculate with it is not so easy, because covering maps with specified branching data are fairly hard to write down explicitly, even for genus 0, where they're just given by sort of a rational function. So a degree n covering map would just be a polynomial of degree n by another polynomial of degree n, and I've written out explicitly the poles, so there would be n poles in general. So there's one way to, so the fact that these are covering maps with specific branching at these points Zi is encoded in the fact that del gamma takes a form like this. It has double poles at these these points lambda a, and it has branching of order W-1 at the points Zi. So one way to compute, there are many ways to compute covering maps, but one particularly nice way that was that was written down by this paper was to sort of requiring that there are no simple poles at lambda a in del gamma gives you a condition which allows you to sort of solve in principle for these the poles lambda a, and therefore effectively the covering map. This is for people who do, these are somewhat like scattering equations in a way, like in the CHY case, and they're not easy to solve in general. As you can see, there are n equations for these lambdas, but there is actually a simplification we noticed at large n, because you can view these as saddle points of a Penner-like matrix model with logarithmic potential, and you can apply matrix model techniques to solve for to solve the theory. In particular, you introduce the so-called resolvent, which captures the density of these so-called eigenvalues, which are really the poles that we are after, the poles of the covering map. And so you can, so then you churn through the matrix model machinery. Basically, the solution of a matrix model like this is encoded in what's called a spectral curve, which is essentially the resolvent, and you shift it by the potential bit. And this spectral curve, in a sense, determines the density of these poles, lambda a, which we are solving for. And in the large n limit, as is familiar in the matrix for matrix models, these poles sort of coalesce into cuts, and if you so we are now talking of a Feynman diagram in which each of these so the covering, the degree of the covering is large, and each of these wi's, which are the number of edges coming out of each vertex, is also very large. They're both scaling proportionally, and so if you recall in my original slide, we had poles in each of these blue faces, and these poles are now sort of coalescing, if you wish, into a cut as the number of big contractions becomes very large, and the spectral curve is effectively like effectively something on a hyperelliptic curve with of genus n-3, where n is the number of points, branch points, and the matrix model is completely solved once I specify the periods of this differential of the spectral curve, and in our case we know what that is, because the number of, it's just the number of big contractions. So the periods along each of these cuts just tells you the number of big contractions along the dual, which are sort of transverse to these cuts, and so once I know these periods along the A and B cycle of this corresponding hyperelliptic curve, in a sense, I have solved the problem. So, at large n, the problem of finding covering maps reduces to solving this matrix model and finding this sort of spectral curve. And the remarkable thing is that this spectral curve differential turns out to be a Strebel differential. Normally, Strebel differentials are very hard to characterize, but here, almost by construction, you get that the square of the spectral curve is a Strebel differential, precisely for the reason that I mentioned over here, namely that these periods, which are essentially the line integrals of of y naught between the zeros of this spectral curve, these are real because these are the filling fraction. They just count the number of Wick contractions transverse to this cut. So by construction, you almost see that for large n, what you have is the Strebel differential coming out of the matrix model curve. And these periods, they take real values. They are just essentially the number of Wick contractions. And of course, in the limit as n goes to infinity, the sum in some sense goes over to an integral over the moduli space. And you see that it's exactly these points. So each Feynman diagram, which I remind you corresponded to a covering map, is now characterized by its own Strebel differential, which corresponds to the point in the moduli space, which in which the Strebel lengths are proportional to the number of Wick contractions of that Feynman diagram. So that's exactly what the philosophy I was outlining earlier was telling you. And moreover, you can actually write the integrand on the moduli space. Remember, this was what Lunin and Mathur had as the Liouville action, the pullback of the conformal map. And it takes a very nice form in terms of the Schwartzian of this covering map. And the Schwartzian, this matrix model spectral curve, all are equal, both are equal to the Strebel differential at large n. Though this equality, of course, gets 1 over n corrections, but the very nice thing at large n is that these very natural differentials, this is another quadratic differential, and this matrix model gives you yet another, and all these quadratic differentials are the same. So this so the field theory seems to suggest that the string theory localizes to these very special points on the moduli space, which correspond to these integer Strebel lengths. But is that really so? And in a way, the very satisfying answer is that from this completely independent perspective of looking at the worldsheet theory of this dual ADS3 system, we arrive at the same conclusion. And this, I think both Matthias and myself and Lawrence, we have talked about it in several places. So I'll just for completeness give you the broad skeleton of that, and also in interest of time. So there, in this tensionless limit, which corresponds to sort of the level 1, where there's 1 unit of NS flux in the ADS3, this most highly curved ADS3 with Nevill-Schwarz flux that you have. There's an old description of Berkowitz-Waffer-Witten, actually for the level K, for the K units of NS flux in terms of a Vesemino-Witten model of the supergroup PSU 1,1/2, which is, if you wish, the geometrization of, I mean, it's the bosonic pieces of that of the ADS3 and the S3. So at level 1, which is what we are interested in, this theory, actually this WZW model simplifies. It has a free field construction, very much like SU2 level 1 has. And this free field construction is in terms of a beta gamma system, if you wish, or 2 symplectic bosons, 2 fermions. The fermions are giving rise to the SU2 like we had. So there's essentially a free field construction. You have to mod out by certain U1s to get to the PSU 1,1/2. The novel aspect of the theory with NS flux is that there, as was known by Maldacena and Oguri more than 20 years ago, is that you have to also include the spectrally flowed sectors of this theory, which I don't have time to explain. But what we find is that these sectors correspond exactly to these twisted sectors of the kind I was mentioning earlier, the ones labeled by these WI. And the most surprising fact is that the worldsheet correlators of the sectors are delta function localized to discrete points on the moduli space, which are exactly the same discrete points that I was pointing out earlier through this Strebel construction. And moreover, you can also argue for the weight associated to this in terms of this sort of Liouville action. Very quickly, just to say this, so this, of course, built on, firstly, the matching of the spectrum between the two sides, as I emphasized in the beginning. So you have this dictionary. Yeah, I probably should skip ahead. There are very special features to the spectrum, which leads to it being a kind of a quasi-topological theory. So you, given the match of the spectrum, you can try to look at the correlators, and there is this unusual localization that we found with Lawrence and Matthias, that the right-hand side is delta function localized to points which admit these, precisely the points which admit these holomorphic covers, the rigid problem that I was explaining to you earlier. While we found this using a somewhat elaborate analysis of the ward identities, which actually then were generalized for arbitrary k, and you have results that I think Lawrence mentioned in last year's string math. But later, using this free field construction, we found that this localization actually follows ultimately from some kind of a twistor-like incidence relation for these twistorial variables, which underlie the free field construction of the level 1 theory. Directly from this sort of incidence relation, you can show that the correlations are delta function localized, which is a fairly unusual feature in a CFD or a string worldsheet. So so just to sort of the kind of capture the logic in some kind of a manageable fashion, this is sort of the open string side that I mostly dwelt upon, which goes from a Feynman graph to these covering maps, and which we analyzed in the large twist limit using an auxiliary matrix model whose spectral curve gave rise to the Strebel differential and the Strebel graph, and the Schwartzian of this covering map also gave rise to this. And this these special points on the moduli space, these integer points on the moduli space, were what the worldsheet analysis also gave you directly and sort of helped to tie this circle. Okay, so maybe I have a minute or two. I'll just very quickly conclude that so inspired by this proposal, we with Matthias, we made a proposal last year for a similar gauge linear sigma model, if you wish, a sort of upgraded version of the ADS3 case to the ADS5 times S5 in terms of very similar twistor or ambitwistor like variables. This not only, I think, had the virtue of being the natural generalization of the ADS3 case, but also fits in with various other indications that these set of variables are very natural from an open string point of view, dating back to the twistor string program for Yang-Mills amplitudes, and also the spin chain integrability where the same sort of variables appear. So since I don't have the time, I just will just sketch what the proposal was. So you have similar twistor-like fields, and we considered an analog of a spectrally flowed vacuum state and these sort of so-called wedge modes for any given W. So this W is now, instead of labeling the length of the cycle of an orbifold, it's labeling the number of bits of your Yang-Mills operator, the number of letters, if you wish, that appear in a Yang-Mills single trace. And so we made the proposal that in a physical gauge, which we are still trying to understand better, most of the modes on the world sheet can be gauged away, and you just are left with these wedge modes. And if you impose some residual physical state conditions, which are fairly natural, have a kind of a natural interpretation in terms of sort of the first one is some kind of a discrete translational invariance on a world sheet with W bits. And the second is sort of a condition, which is a kind of a U1 projection, and which basically says that you look at singletons. So this, if you take these physical states with this sort of physical condition, then that reproduces precisely the single trace operators of n equals to 4 Yang-Mills in the free limit. And they're basically built out of these letters of the free Yang-Mills theory. And but we are, so it gives a very natural organization of the free Yang-Mills spectrum in terms of these bits built out of these twister. These are actually the same bits, building blocks of the integrable spin chain as well. So that's very encouraging for us. But the world sheet quantization that reproduces these physical modes as the only physical ones and the residual constraints, something we are trying to work out. But we expect many things, many features of the ADS3 to go through. In particular, if you, I don't have time, but in a sense, the Strebel construction, there's a very natural Nambu-Goto area associated to them, which gives rise to the free Feynman propagators, again, through a Schwartzian of a covering map in twistor space. So yeah, so let me just conclude. I'm sorry for going over time. Just to summarize, we exhibited this test case where this general program for assembling large N gauge theories or QFTs into string theories can be explicitly carried out. And we could close the circle in this case from strings to fields as well, because the world sheet theory was tractable. We are looking into the extension to n equals to 4 Yang-Mills and to other large N gauge theories, for instance, to engineer the string duals to even basic large N matrix models is something we are doing with Edward Mazenk. So to this audience, I just want to convey the overall message that this tensionless string theories are likely to give a very unusual family of topological string theories. And I think there are many interesting connections to maths as well, which I could only allude to, but I'm happy to talk about later. So thank you very much.
Thank you very much for the wonderful talk.
Tired, maybe we should be going on to thanking all the organizers.
I think we should think once again.
So as I said, as the last speaker, it's my sort of a duty and a pleasure to thank all the organizers. I know, of course, mainly of the scientific organizing committee, which consisted of Pavel Kaputa, Zygmunt Lalak, Adrian Langer, Miloš Panfil, Jacek Pavelčík, Rafal Zuzak, and of course the chair, Piotr Sulkowski. I'm sorry for mangling up the names, but let's give them all a great hand. And maybe I'll invite Piotr to tell us about all the other people who helped to make this a wonderful success.
Yes, thanks a lot. Again, I will still keep you here for a minute or two, because I'd like to thank well, everyone who made this conference great. So first of all of you who came here and were here, first of all in person, but also online. I hope you are still, some of you watching us online. So thanks a lot to all of you again. I already said that, but I will repeat the fact that we are here in this group of people is the something that we owe to the steering committee who agreed to organize the conference here, the scientific committee who worked very hard to choose great speakers that we heard, the local committee, we already heard who was in that, and I hope that in the meantime you got to know everyone of the committee. But then there were also many people who have not been named yet, and they did a lot of hard work. Some of them you see here sitting in front rows. They were recording the lectures and operating Zoom and made everything work. So here you see Pedram Karimi, Sinon Kriu, Dmitry Noschenko, Elder Lara Givel, Xi Chang is there. Aditya Bhavane, I'm not sure if I see Aditya, but he was also here most of the days. Dongsheng Ge, Felipe Santana, Dimitrios Patramanis. There was also hardworking administrative staff, Marta Kowol, Anna Ciesielska, Luisa Wiślicz. They are not here with us, but they were with us, well, virtually most of the time. So we have to remember all these names. And of course, the people who are running this lecture room with all these facilities and this department. So I think we should thank all of them. Let me remind that before you leave, you still can take these posters which are all here, and also the bags. There are some bags, especially if you bought more things in Warsaw. You can even have the second bag if you got one already. So they are here. By the way, there is something that one of you might have left. So just in case, if you have not noticed, you may take that. And to finish, let me say that the conference will not quite be over yet. The web page will still be updated. We will post all the missing videos. You might have seen the photographers around, so we will also somehow share the conference photos with you. And there is a plan to have proceedings. Probably they will be published just in a couple of years. This is how long this publishing process takes, but still, if you missed some details of some talks, then probably you may find them in these proceedings in some time. And finally, hopefully many of us can meet next year in Melbourne. Yeah, so thank you.